All right, let's move forward in section 3.3 and talk about instantaneous rate of change. Okay, so instantaneous rate of change is one of the most important concepts in calculus. So to motivate this topic, let's consider this scenario. When a stoplight turns green and a car begins to accelerate, its speed increases over time until it reaches the speed limit. Okay, hopefully the speed limit, right? Suppose that the distance traveled by the car is given by this function s of t. And yeah, s, for some reason, that's usually the letter that we use for a position function. Okay, I'm not sure why it's s. Maybe it's from Latin or something like that. But anyways, a position function is often given as s of t equals. Okay, and 3t squared for t between 0 and 15. Okay, so this function just defined between 0 and 15, where t is seconds and the distance is in feet. Okay, and then note that speed can be thought of as distance divided by time. Okay, so like for this one, it'll be feet per second, but a lot of times you might think about miles per hour. Okay, but for this function, it's modeling feet per second. Okay, now we know that in order to find the average rate of change, which would be your speed, we can find the average rate of change of the car over any time interval. Okay, but we want to determine the exact speed of the car at a particular instant, okay? That's the instantaneous rate of change. So in the previous section, we could have found what's the average rate of change of this car from time t equals 10 to time t equals 15, something like that. But we're interested now, what is the exact speed at a single instant? Okay, so let's think about this. The idea is that the exact speed at t equals 10 is going to be very close to the average speed, the average rate of change, over a very short time interval near 10. Okay, so to save some time, I have all the calculations already outlined in this table here, but let's consider a time interval that's really close to 10. So from 10 to 11, for example, pretty short interval right there of 1 second. Well, if we worked out the average rate of change formula, s of 11 minus s of 10 over 11 minus 10. Now these numbers, these are all calculated using this function right here. Okay, so plugging in those values. So we get an average rate of change and we get this average speed of 63 feet per second. Okay, so that's the average speed from this interval. Okay, but we want to get it as close to 10 as possible. So let's go 10 to 10.1, just a tenth of a second. Okay, work out the average rate of change formula and it comes out to 60.3. Let's get even better. How about 10 to 10.01? Okay, work out the whole formula, being really careful, and then we get 60.03 feet per second. And even closer to 10 to 10.001. Work out the average rate of change formula and we get even closer. And doesn't it look like it's sort of approaching something? All right, and so if you're imagining that there is some kind of a limit involved, you would be correct. What does it look like this is approaching as this interval shrinks and goes from 10 to 10.000000001? Like really let this second number get closer and closer to 10. It looks like the average speed is getting closer and closer to 60 exactly. We got decimal places going way out there. So yes, the results in the chart suggest that the exact speed at 10 is 60. It looks like it's approaching 60 when we let that interval get tinier and tinier. So we can confirm this algebraically by computing the average speed from t equals 10 to, and then we'll let the second endpoint of the interval be 10 plus h, where h is not 0, but it's just really small. Okay, so like 0.1, 0.01, 0.001. Okay, so it's not 0, but it's really small. Okay, when that number is going to just represent a very small change in time. So here's the algebra behind it, and I'll just kind of talk through this right here. But if we did the average rate of change function, so this is f of b minus f of a over b minus a. And again, I said f, but whatever the function name is. Okay, so 10 plus h minus s of 10 plus h minus s of 10 over 10 plus h minus 10. And if we work that out, we got to plug it into the function. Now remember the function said 3t squared. So that's got to be plugged in and that's got to be plugged in. And then 10 plus h minus 10, notice that the 10s will cancel and we're left with just h down there. Okay, then we got to work it out, be a little bit careful. Remember that when you have a binomial that's squared, you have to write it twice. and FOIL it out. So I have it written twice there. We can start simplifying some of these numbers. If we FOIL out 10 plus h, we get this expression. Go ahead and distribute that 3 in after you're done with that. And then we get all of this. Some nice cancellation happens here, 300 and minus 300, so those are gone. And so we're left with just 60 plus h, or 60h plus 3h squared on top. And then notice another nice thing is they have a GCF of h in the top, so we can factor out an h, and then very nicely, we can factor out that h, and then we can cancel that h. And we're left with this 60 plus 3h result. Okay, so remember that h is not equal to 0, but we want it to get closer and closer to 0 so that the time interval from t equals 10 to t equals 10 plus h gets closer and closer to a single number. Therefore, the exact speed at t equals 10 is, like we thought, the limit as h approaches 0 of the average speed over the interval from 10 to 10 plus h. All right, and this is just awesome the way that this ends up working. So the limit as h approaches 0 of that average rate of change, which we already calculated up there, it comes out to 60 plus 3h. Remember, h is not actually 0, but we're doing a limit as we let h go to 0. And when we evaluate limits, this is just a polynomial here. We can go direct substitution. And so 60 is unaffected, and then 3 times 0, this is approaching 60 feet per second. And so this is like kind of a proof of what the table was showing us. We were thinking as we let this interval get smaller and smaller and smaller so that it seems like it's including just a single point at t equals 10, it looked like it was approaching 60. And if we use that formal limit notation here, then it is 60 feet per second exactly at t equals 10. Awesome stuff. And then of course we want to generalize that. So this process is generalized as follows. And I put a big box around this, very important topic here, the instantaneous rate of change for a function f when x equals a is, the limit as h approaches 0, f of a plus h minus f of a all over h. Okay, and provided the limit exists. Okay, so you saw how sometimes limits don't exist, and we'll return to that possibility a little bit later. Okay, but yeah, pick a value a. If you want to find the instantaneous rate of change of a function at a single point, it ends up being the average rate of change function as we do this limit as h goes to 0. Absolutely awesome. So keep in mind, and maybe I haven't said this exact phrase right here, but the expression inside the limit, okay, so that's this part, the average rate of change part. That's called the difference quotient, especially if you have f of a plus h minus f of a over h. That's called the difference quotient, okay? And it's equivalent to the average rate of change formula, okay? And then the instantaneous rate of change is then the limit of the difference quotient. Okay, and to help us kind of visualize everything that's going on here, because there's a lot going on here, and this concept is extremely important, I want to take a look at Desmos. So the link right there, I already have this built in, so all of this stuff is entered, so you can follow that link and have this same display. So what this is, let me kind of explain what all of this fancy stuff is over here. I have the function graphed s of t equals 3t squared, so that's the function graphed, and we're only considering t greater than 0. Okay, so here's that function, and so this is just giving us the position. I have this expression here labeled as L for limit, but right now it's not a limit because this is the average rate of change, s of 10 plus h minus s of 10 all over h. But right now I have h, and this is the great thing about Desmos, I have h set at 5. Okay, so what the image over here is doing, the projector mode makes it kind of too bold. Anyways, what's going on over here is I have the different points plotted. So at 10, okay, at a t-value of 10, s of 10 comes up here, and that's plotted on the graph. Okay, and then right now I have h set at 5. So if we think about the point 10 plus 5, well, yeah, that's over here at 15, 10 plus 5, and then is plotted on the graph up there. And so we can think of, like I was saying, the average rate of change, you could think of that as the slope between the 2 points on the graph. And so that's this black line that I have drawn through here, that's a line that would connect those 2 points. And the average rate of change between those 2 points is the slope of that line that would go through those 2 points. okay? And so the whole point here is for the instantaneous rate of change, remember that we want the limit as h goes to 0. So right now I have h set to 5. If we make h go to 0, I use this little slider, and notice what's happening. We get that those two different points are getting closer and closer and closer, and notice that it changes kind of how that line looks, the slope of that line. It's getting like a little bit like flattening out a little bit. And so as we let h go to 0, these 2 points are getting closer and closer and closer. And so the time interval should be getting less and less and less. And actually, I think we did one of these. If I let h equal 1, then that means it's from 10 to 11. And I believe we had that one calculated from 10 to 11, and it shows 63 feet per second. Okay, so that matches up. But we want it to go to 0. We want h to go to 0. We want these 2 points to lie right on top of each other. So let h go to 0, let it go to 0, and boom. Right there, the two points lie right on top of each other. Now notice that the limit thing that I wrote up here, it says undefined. And the reason for that is if I let h be 0, and right now it's dividing by 0, so Desmos can't really handle this, but we can. Okay, so what's actually happening here is once h is 0, this is now the limit. And we did that fancy algebra canceling, and it came out to a nice number. So down here I have, don't worry about this notation quite yet, but this little notation right here is the actual instantaneous rate of change right at 10, and it is in fact 60. Okay, so the calculus is kind of a little bit of a loophole for this divide by 0 problem. But the idea here that I just really wanted to emphasize, and we're definitely going to come back to this instantaneous rate of change in more detail in even the next section, but I really wanted to emphasize that the average rate of change just imagines that there's 2 points that are spread out somewhere on the graph, and the instantaneous rate of change, we want to make it so that the difference in those 2 points shrinks all the way down until they're pretty much just a single point. Okay, cool stuff. All right, let's continue. Man, that's just awesome stuff. So in the previous example, we saw that the instantaneous rate of change of a position function gave the speed. Okay, but speed is always positive. You want to imagine that you're always, moving. If you're in your car, you always talk about a positive speed that you're traveling at. But if you actually worked out that instantaneous rate of change, especially if it's some other kind of function, you could end up with a negative slope or a negative instantaneous rate of change somewhere. Okay, and so therefore, if you're working with problems where you're talking about like the speed or velocity of something, the velocity by definition, we're going to refer to the velocity when we want to consider not only how fast something is moving, but also in what direction it is moving. Okay, so in any motion along a straight line, we usually just label movement to the right as a positive number velocity to indicate that it's moving to the right. And any movement to the left is indicated as a negative number for velocity. And then since speed is always considered a positive number, we just define speed to be the absolute value of velocity. Okay, so something to keep in mind there, speed is the absolute value of velocity. Velocity is the instantaneous rate of change of a position function. And so some examples like that could come up later, and we'll just talk about that in more detail a little bit later. An alternative form for the instantaneous rate of change for a function f when x equals a can be written like this. Okay, so for this one, we can think of, we're picking a, we want to find the instantaneous rate of change at a specific a value. Okay, but then any other b value, and you don't actually pick a b number, this b is kind of like the h where you leave it as a b. But you imagine that like some other b value, and it could be like larger than a, or it can be smaller than a. It doesn't matter if it's on the right or the left. But you just work out this formula, and we just imagine that the limit as the b number approaches the a number, which is the same concept, right? We want to make sure that these 2 points, they start apart from each other, but the limit as those 2 points actually approach each other and end up lying right on top of each other. Okay, so it's the same formula, just in kind of a different way. Okay, just letting the b number approach the a number. And if you work out this formula here, it'll give us the same answer. It's just an alternative method of doing it. I prefer the one that has the H involved because that's the one I think it's used more frequently, and it's the one that I've used my whole life. So I'll show you how to use both in the next example, but I'll definitely make a separate video to do example 4.